And the next system that I want to talk about is a metamorphic reaction, a very common metamorphic reaction in rocks that contain silica and an abundance of calcium. You could imagine taking a limestone plus some sandstone, mixing it all together, and you might have the set of reactions we describe here. Okay, the reaction is this. On the left side of the equation, we have grossular garnet plus quartz. Those two react together to give anorthite plus wollastonite. Anorthite, there's the calcic plagioclase, and wollastonite, that's a peroxenoid. It's the calcium end member on the ternary of the pyroxenes. Okay, we can use some abbreviations, and we'll start abbreviating most of these phases with smallest number of letters to be a unique representation. So we have grossular plus Gr plus Q going to An plus wollastonite, WO. And to balance this equation, for every mole of anorthite, we need 2 moles of wollastonite. And now let's look at the chemical formulas associated with this reaction. And here they are. The grossular garnet, it's got calcium and aluminum plus isolated silica tetrahedron. You know they're isolated because it's Si3O12. That's a 1:4 ratio. Then you have quartz, just the simple SiO2. Then on the right side of the equation, we have anorthite. Check it out. It's got the calcium, aluminum, and silicon, and it's got the framework ratio of aluminum and silicon to oxygen. And finally, wollastonite on the far right, you have 2 in front of that. We need 2 of those for every 1 of the anorthite, and it has calcium plus silica in the Si to O ratio of 1:3. The pyroxene ratio, but wollastonite is what we call a peroxenoid. So how many chemical components do we need in this system? Well, we have calcium, we have aluminum, we have silicon. There's 3 components. Of course, we also have oxygen in the equation, but oxygen is found in all the equations. So we can get away with trying just oxides of those 3 cations. So we have CaO, SiO2, and Al2O3. Those are chemical components. Can we build all those phases out of those 3 chemical components? Well, let's try it out. Here is the garnet, the calcium aluminum silicate. Well, there's 3 calcium, so we need at least 3 CaO. There are 3 silicons, so we need at least 3 silica units. And there's 2 aluminums, which gives us 1 of the alumina units of chemical composition. Okay, so that takes care of the cations. Add up the oxygen anions, and you'll see they add up to 12. So in fact, these building blocks do add up to grossular garnet. We go through the same exercise for the plagioclase, for the anorthite, and in this case, 1 calcium oxide plus 1 aluminum oxide plus 2 silicon oxides does the trick. And again, the oxygens add up correctly. For the wollastonite, we have calcium and silicon, so we just add 1 unit of a calcium oxide and 1 unit of a silica building block, and that gives us the right number of calcium, silicon, and oxygen. So we have 3 components that build all the phases of this system. Once we know there are 3 components, we can write down the phase rule. We substitute in 3 for C, and that gives us number of phases equal to 5 minus the degrees of freedom. For degrees of freedom of 0, 1, and 2, we have either 5 phases, 4 phases, or 3 phases as being possible in this system. Well, let's look at the phase diagram in pressure temperature space. I'll remind you up at the top what the chemical reaction is. And I'll remind you that our analysis says that along univariate phase boundaries, we could have 4 phases. Along divariant regions of the phase diagram, we could have 3 phases. So let's draw in pressure temperature axes. There they are. Let's put in a line which separates the region in which anorthite and wollastonite are stable from the region in which grossular and quartz are stable. This white line is the reaction line. We take a bit of anorthite plus wollastonite at low temperature and we heat it up to the reaction line, and it will react to form grossular garnet plus quartz. Now, we already see a connection with the phase rule here. Along the univariant phase boundary, the phase rule says that there are 4 phases that can be in equilibrium, and as drawn here, you'll notice there are 4 phases in equilibrium at that point. Now, we call this structure in pressure temperature with reaction lines on it a petrogenetic grid. It shows in pressure temperature space where all the important chemical reactions occur. And we can take the example then going from point A down at low pressure to a point B at high pressure, the red line showing a path in which pressure is increasing at constant temperature. This would be an effect of burial, pushing it down farther in the earth to greater depth. Now, as you pressurize it, it crosses the reaction line, so there has to be some changes in the phases. So at point A and point B, let's track what's going on, and I have the table at the bottom. So let's first of all take a calculation assuming that we have 1 mole of anorthite and 2 moles of wollastonite. From the chemical formula at the top, you can see that 1 mole of anorthite and 2 moles of wollastonite will react to form 1 mole of grossular garnet and 1 mole of quartz. So for that chemical composition, we have this outcome. What's going on here? At point B and at point A, we only have 2 phases present, yet over in our phase rule it said that we could have 3 phases. We need to explore this a little bit more. So let's take another composition. And for my second composition, I'll take 1 mole of anorthite and 3 moles of wollastonite. So I've added extra wollastonite to the system. Now when I react anorthite and wollastonite together to make grossular and quartz, what's going to happen is we're going to use up 2 moles of the wollastonite to make the quartz and grossular, but we're going to have a mole left over according to that chemical reaction. So now there are 1 mole of grossular, 1 mole of quartz, and 1 mole of wollastonite at point B. Aha! We are in accord with the phase rule. 3 phases present at point B. Let's take another composition. Instead of 1 mole of anorthite, let's put in 2 moles of anorthite plus 2 moles of wollastonite. React this through the given phase transit, given reaction, chemical reaction at the top, and you see that we end up with 1 mole of grossular, 1 mole of quartz, and 1 mole left over of anorthite. We had an excess of anorthite that couldn't react with anything, so it still exists. So it's 3 moles, or it's still 3 phases present at point B, but it's a different collection of 3 phases. So the analysis here tells you that the phase rule gives you the maximum number of phases that can exist at any point in pressure and temperature. It doesn't tell you what the minimum number. The actual number of phases will depend on the bulk composition of the material. The actual number and which ones are there depend on the bulk composition. So let's follow this a little bit farther on now. And what I'll do is I'll color in the 2 regions. The yellow area for the higher pressure regime and the blue area for the higher temperature regime. And now what we have to do is look and see what minerals are present in those 2 areas. And of course, that's going to depend on the starting composition that we are using. So for instance, if in the blue area we have 1 mole of anorthite and 2 moles of wollastonite, then in the yellow area we're going to have 1 mole of grossular garnet and 1 mole of quartz. So the correct phase diagram showing here is grossular plus quartz at high pressure and anorthite plus wollastonite at higher temperatures. However, if I switch to more wollastonite, I still have anorthite plus wollastonite stable at low pressure and high temperature, but now in the yellow field I have three phases present: grossular, quartz, and wollastonite. And if I change the composition again to the third example, then in fact in the yellow area I have grossular, quartz, and anorthite present. So which phases are present in each of these fields depends on the bulk composition. When I show you a pressure temperature plot with shaded areas in different colors and with different minerals shown in each of these areas, what I am showing you is a pseudo-section. A pseudo-section is a projection of phases, for this multi-component system down on 2 dimensions, and I've done it by assuming a bulk composition for the rock. Okay, so petrogenetic grids show us where the reactions occur. Pseudo-sections show us what phases are present depending on the bulk composition assumed in making the calculation.